and I'm going to talk about the location of the equilibrium points. If I look back at some previous notes, I've talked several times about this potential energy and how the critical points of this is called the effective potential. So the critical points of the effective potential energy are where there are equilibrium points. But let's look at that from a different point of view. And also, this is only in z equals 0. So in the study of dynamical systems, if you're to do an analysis of a nonlinear system of ODEs, one of the first places people typically start is looking for equilibrium points. So it's natural for us to look for equilibrium points even in this system. So that's what we want to do. And we're looking at equilibrium points in the rotating frame. So in the rotating frame, we seek equilibrium points. So these would be points where there is no motion. So in general, if I were to write a nonlinear ODE that's time independent, x dot equals f of x, where x is in Rn, equilibrium points are those points, I'll call it x bar, where x bar dot equals 0, the vector 0. So there's nothing happening at that point. There's no motion at all. So that means we can look for points x bar such that f of x bar equals the 0 vector. That's what an equilibrium point is. You first have to find equilibrium points before you analyze the motion near them. And that is what we're looking forward to, is we're going to look at the motion near equilibrium points, especially the 2 points that are near the secondary mass and are becoming more and more important for space missions and design of low energy trajectories. For the circular restricted three-body problem, or CR3BP, the usual equations that we've been looking at, the equations in first order form, look like the following. X dot equals Vx, y dot equals Vy, I'll include Z, and then Vx dot equals 2Vy minus that partial derivative of the effective potential function. So I'll write that as U bar sub X. So my notation is that U bar sub Qi just means it's the partial derivative of that with respect to that variable. Vy dot is negative 2Vx minus partial derivative of the effective potential with respect to y, and Vz dot equals just negative partial u partial z. Okay, so those are our equations of motion. An equilibrium point will have, right, x dot, y dot, z dot, and then all of their time rates of change of the velocities, in other words, the accelerations, equal to 0 in the rotating frame. So we want that, which means we could look at the right-hand sides of these 6 ODEs and just set them equal to 0. So this implies that the velocity in the rotating frame is equal to 0, which is kind of obvious. If you've got a point that's equilibrium, then there's no velocity. So in the rotating frame, the velocities here are all equal to 0. Those are 0. But then we also want no acceleration. So all of these have to be 0. Well, we've already lost, if Vx and Vy are both 0, then these terms are already 0. And so we're just looking for where U bar X and U bar Y and U bar Z. So the partial derivatives in all the directions equal 0. If you have a scalar function and the partial derivative is 0 in all directions, we would say that's a critical point of that function. So we're looking for critical points of the potential energy. Hopefully you've heard that term. The effective potential energy. Now, there are no critical points when z is away from 0. you'd have to take the partial derivatives to look at that, but when z does not equal 0, there are no critical points. That means there are no equilibrium points that are out of the plane of the two primary masses. Right? We're looking at, there's two masses, M1 and M2, moving in circular motion about their common center of mass. All of the equilibrium points, if they exist, and they do, are in the plane of the two bodies. So we need to look at z equals 0. So if we consider z equals 0, we don't even really have to consider the z equation. So we'll just get rid of the z stuff from now on. So if we look at z equals 0, that means we're just looking at a critical point in the xy plane. So where those equal 0. And there are some that exist. So this is in the plane of the two bodies, M1 and M2. Remember, M1 is the bigger one, and then M2 is the other one. If we look at the potential energy function, and I'm just showing it big here again, this is when z equals 0, you do have critical points. So there's points where the partial derivatives will equal 0. So looking at that, we'll start with the easier ones first. The easier ones are solutions that have y not equal to 0. We're looking at z equals 0. Now let's restrict ourselves to y not equal 0. If I do a little sketch of our system, remind ourselves, we're looking in the xy plane. We've got the mass m2 over there and the bigger mass m1. So this is at negative mu 0. And this is at 1 minus mu 0. And if we're looking at y not equal 0, that means we're looking off of the x-axis. And looking off of the x-axis, it actually makes sense to consider, for point P, instead of using x and y, we can use the distance to the point M1 and the distance to the point M2. So instead of x and y, we'll use R1 and R2 as our variables. So this is kind of like what the Lagrangian approach does, where you can use different variables. You could use different coordinates. These are generalized coordinates. So we'll use R1 and R2 as the variables. We've written U bar before. It looks like negative, there's the gravity terms. And that's the non-dimensional mass of M1. And then this is over R1. And then the non-dimensional mass of M2. And that's over R2. And then we've got the terms that are related to the centrifugal force. And those are negative 1/2 x squared plus y squared. And here's what we're going to want to do. When I made that plot, I was thinking of the effective potential written in terms of x and y. But what we'd like to do is write this in terms of R1 and R2. But that means we need to write x squared plus y squared in terms of R1 and R2. And fortunately, we can do that. What is R1? Well, let's do R1 squared. R1 squared is the distance from the point P to M1. So that's going to be x minus mu, or we just write that as x plus mu squared plus y squared. And then R2 squared is x minus 1 minus mu squared plus y squared. Because we're setting z equals 0. We've already established that if there are equilibrium points, they have to be in the xy plane. So z is 0. So we've got those two. Oh, this is the squared is in the wrong place here. There it is. Here's what I'm going to claim, and it'll actually make life easier if we can work this out. I'm going to claim that x squared plus y squared equals 1 minus mu r1 squared plus mu r2 squared minus mu 1 minus mu. Oh, and that does remind me, I am missing something from this u bar, and it's that constant term that we just sort of kept around. There was some term added, minus 1/2 mu 1 minus mu. So that's in there. But I've got this claim down here that we can write x plus y squared in terms of R1 and R2. You could work this out and see that it's true if we do, say, 1 minus mu times x plus mu squared plus y squared plus mu x minus 1 minus mu squared plus y squared. So that's just the first two terms. What do we get from that? If we expand it out, we'll have x plus mu squared plus y squared minus mu. And now maybe I'll just expand this out. X squared plus 2 mu x plus mu squared plus y squared. That's what I get from here. And now let me add the other part. So plus mu and expand it out. X squared minus 2, 1 minus mu x plus 1 minus mu squared plus y squared. And maybe you could already see that some things will cancel, right? This is a minus mu and this is a plus mu. So for the y squared things, mu times y squared, so these will go away. Mu times x squared, those two will go away. Let's just write the rest of it out. So this will equal x squared plus 2 mu x plus mu squared plus y squared minus 2 mu squared x minus mu to the third. And then I'm down here, minus 2 mu x minus, plus 2 mu squared x plus mu 1 minus mu squared. And now let's look for some other things that cancel here. We've got 2 mu x and minus 2 mu x, minus 2 mu squared x and plus 2 mu squared x. Looks like we'll have to keep on going here. I'm going to get x squared plus y squared plus mu squared. And what's this last thing? Mu times 1 minus 2 mu plus mu squared and plus mu minus 2 mu squared. I had a mu to the third from up here that I didn't include, minus mu third, because it cancels the plus mu third. Okay, so those go away. So this equals x squared plus y squared plus mu minus mu squared, or x squared plus y squared. Ooh, how would we write that? Plus mu 1 minus mu. So we have what we want. This claim is true. Got this extra thing, which if you subtract it off, then boom, it's up there. So this claim is true. We can rewrite x squared plus y squared in terms of R1 squared and R2 squared. That's all we really wanted to do here. Okay, so if we do that, then we could look at u bar as a function of R1 and R2, and it will be minus 1 minus mu over R1 minus mu over R2, and then minus 1/2 x squared plus y squared. We will get minus 1/2 1 minus mu R1 squared minus 1/2 mu R2 squared. Let's just leave it at that. So now we've written our effective potential, but in terms of R1 and R2. Great. Using the chain rule, you can show that it doesn't matter which variables you use. U bar, written in terms of R1 and R2, or written in terms of X and Y, will have the same critical points, as long as Y does not equal 0. If I write out U bar, so partial U, partial X, but now consider that R1 and R2 are also functions of X. So we could write this as partial U bar R1, partial X, plus partial U bar R2, partial X, we could write out what partial R1 and R2 are. So this is U bar R1, and partial R1, partial X is just X plus mu over R1, and then U bar R2 times X minus 1 minus mu over R2, and we want that to be equal to 0. We do something similar, writing partial U bar, partial Y, and it'll look very similar. It's just now it's partial R1, partial Y, plus U bar R2, partial Y. This is U bar R1, Y over R1, plus U bar R2, Y over R2 equals 0. So those are the equations we want to solve. This is all to show that U bar X equals U bar Y equals 0 is equivalent to U bar R1 equals U bar R2 equals 0. They'll give the same thing when Y does not equal 0. So that means these terms are non-zero. So as long as we're not on the x-axis, we can look at U bar as a function of R1 and R2 and set those equal to 0. We want to solve the following system of equations. U bar R1 equals 0. And from the way that U bar is written up there, we could just take the derivative of U bar R1. U bar R1 equals 1 minus mu R1 minus 1 minus mu R1 squared. Well, we pick up a plus. So I think this is a minus and this is a plus. Okay, so we have that. And then U bar R2, which is minus mu R2 plus mu over R2 squared. And how can we solve this? If you look at this, we need both of those to simultaneously be 0. Let's just start with the first one. The first one, it only is a function of R1, and there's a 1 minus mu. So we could just sort of cancel out that. And so we've got 0 equals minus R1 plus 1 over R1 squared. Move the R1 over, some of the R1s cancel, and we get that R1 has to be 1. And for this other one, similarly, we get that R2 needs to be 1. So there is critical point at R1 equals R2, both equal 1. Okay, well, now we can try to geometrically figure out where this is. I'll write it using the usual coordinates of X and Y. So M2, here's M1. Remember, they're a distance 1 away from each other. Distance between the two is 1. We put that up here. And we're looking for the location where R1 and R2 are both equal to 1. So hopefully you can see where these are. It would be at these points. So at this point, this is R2 equal to 1 and R1 equal to 1. So it would be that point. That's one of these equilibrium points. Of course, there's a mirror image solution if you look below the x-axis, where again, both of these are equal to 1, R2 equal to 1, R1 equal to 1. And hopefully you can convince yourself, if you try to move these points anywhere else, there's nowhere else. There's just these two equilibrium points. There are two locations that satisfy this criterion, and they're two equilibrium points. Remember, we're only looking in the XY plane. If we could do something out of plane, but we can't, they just won't be equilibria. So these two have come to be called L4 and L5. So this point up here is L4, and this one down here is L5. And you could see the three masses, say, look at L4. The three masses are at the edges of an equilateral triangle where all sides are equal to 1. So these are called either the triangular solutions or they're called the equilateral points because they form an equilateral triangle. So they are also known as the triangular points. And this was known to Lagrange, and that's why we call these Lagrange points. So there's L4 and L5. It's also was also found by Lagrange that you could have something of a non-trivial mass there. So we're looking in the restricted problem, but suppose you had something that was actually massive and might influence M1 and M2. The equilateral configuration is still an equilibrium, even when you get rid of the restriction that makes it the restricted problem. So you could have a massive M3 there, and this would still work out. So it's possible that there are star systems out there where maybe we have 3 stars at these points of an equilateral triangle. They're pretty robust, since you could have even a larger mass there. So these are the L4 and L5 Lagrange points. It's not obvious from where they are, but it turns out that for most values of the mass ratio of M1 and M2, particle at L4 or L5 will be stable, or a particle that's displaced somewhat from L4 and L5 will just sort of oscillate around it. So they are stable points, but that's not obvious from what we've done here. You have to do something additional. You have to linearize. So that's the common thing one does after you find an equilibrium point of any nonlinear dynamical system. You find the equilibrium points, and then you look at the ODEs linearized about that point. So you get a linear system. You'll get, in this case, if this is a 6 dimensions, right, 3 position, 3 velocity, we would get a 6x6 square matrix. And based on properties of that matrix, looking at eigenvalues, you could determine the stability type of the equilibrium points. And these will turn out to be stable equilibrium points for most values of mu found in the solar system. If the mass ratio gets too large, those points actually become unstable. And that's kind of interesting. It's also interesting they're stable because they are maxima of that potential energy function. They're local maxima. In fact, they're global maxima of the potential energy function. They are the critical points that are maximum in the XY plane. And yet these are stable points. So our intuition about looking at energy doesn't quite match that. We would expect something stable if it's at some lowest energy state. But there is no lowest energy state here. The lowest energy state is actually at the location of the masses M1 and M2, where it's infinitely deep. You're at a singularity. So those are out. What's going on is that we're in a rotating frame. And when you try to analyze stability in a rotating frame, you can't just use the idea of maximum or minima of a potential energy function. You've got to do something else. We'll do that later. So those are the easiest ones to find. And maybe it wasn't so easy. There was quite a bit of algebra just to write x squared plus y squared in terms of R1 and R2, but we did it. There's been some interest in L4 and L5. I think there was like a L5 society where they wanted to put a space station at L5 in the Earth-Moon system. So if you think about that, I mean, so L5, they want to put something there, and it is the same distance away from the Earth as it is from the Moon, which for our purposes, in terms of the way that the commercial and government interest in space is going, it's not quite clear why you'd want that. It's not easy to access from either the Earth or the Moon. So you could put a station there, but I'm not really sure why, if you want to have easy access to the Earth or Moon. So the other points that people have been interested in are the collinear points, collinear solutions. So if we now don't restrict ourselves, we're going to look along the line of primaries.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series. There are links and other materials in the description.